Okay, so here we are in activity 3. We're going to talk about effective nuclear charge. And we're still looking at how can categorizing elements by atomic structure help us to make predictions about their properties. Okay, and our learning target is I will use the atomic structure of element X to determine its placement in the periodic table. Okay, so think back to maybe 6th grade, maybe 9th grade. Remember when we learned about like how charged particles, when they meet each other, what happens? And we learned that if they're the same charge, they push each other away. But if they're the opposite charge, they pull each other towards each other. And so that is very true, but there's a lot more to it than just that. Okay? Really, what we see is that there are actually other variables that affect the attraction of opposite particles, like electrons and protons. Okay? Particles of like size attract each other equally. So a proton and an electron in the same spot will equally pull on each other. Okay? Particles of different sizes we find that the large one attracts the smaller one more. So something bigger and something smaller, that smaller one's going to feel that bigger one pulling on it more than the other way around. Okay? And the further away the particles are, the lower the strength of the attraction. So earlier I said that particles of the same size attract each other with the same amount of force. Well, if you move those farther apart, that force becomes smaller and smaller. Okay? So the farther they are from each other, the less attraction they feel. Okay? And so here's some of the reasons why. The first one is the shielding effect. So the closer an electron is to the nucleus, the more attraction it feels, right? Because the farther away, the less it feels, the closer together, the more it feels. Okay? And so electrons in completely filled shells, we call core electrons, they experience more attraction than the valence electrons. Okay? So here's our core electrons. And because they are closer to the protons, they feel more attraction than the valence electrons that are on the outside. Okay, so let's look at magnesium. Okay, so this is a magnesium atom. There are 12 electrons in the center, and there are 12 protons in the center, 12 electrons on the outside. And so if we look at the shielding thing, if we think of this electron is actually going to cancel out this proton. And this electron is going to cancel out this proton. Okay? Then again, this is a full shell. So this electron cancels this one. This electron cancels this one cancels this one, and this one cancels this one, right? So we have here where we have just these two protons and we have these two electrons, but those two electrons are much farther away from the protons. So these electrons are kind of hiding the outer electrons from the protons. So that's what makes the effective nuclear charge so important. Okay, those core electrons then shield the valence electrons from some of the attractive force of the protons. Okay, so this all leads to what's called the effective nuclear charge, which is the net positive charge experienced by the valence electrons. Okay, so basically what we're looking at is that the effective nuclear charge, they call that Z, and so ZEFF is equal to the nuclear charge, right? So the number of protons minus the shielding electrons, so the core electrons. So if we were to, like, so this one is for sodium. If we were to look at oxygen, oxygen has 8 protons, and its shielded electrons, there are only 2. So that very first shell is filled in, but the outer shell is not. So we only have 2 of those core electrons. So that gives us a positive 6 for our effective nuclear charge. Okay, so now you should be able to look at the effects that the protons and the the protons and the electrons have on each other, and be able to bring that also to placing elements in the periodic table.